Hi everyone. Welcome to this new Accretion-Ejection talk, the first of the year. So we are really happy to have Adnan. He's a postdoc at Lyon, at CRAL. He did the PhD at CEA Saclay in France, and he will present his recent work performed with Asmita Mandare and Benoît Commerson on protostellar accretion. So feel free to start when you want.
Okay. Well, thank you very much, Raphael. This work here is a letter that started off as a collaboration between myself and Asmita. So basically, what we had were two different models, both treating the same subject, which is the birth of a protostar. And what we wanted to do was to sort of answer sort of a long-standing question in star formation, to which we had a lot of answers already, but nothing that was um, quite um, quite as much, quite as convincing as a grounded proof, which was the radiative efficiency of protostars. So just to begin here, what actually is the radiative efficiency of a protostar? So protostars, well, they mainly shine by radiating away the kinetic energy of the gas that they accrete. And the reason for this is that protostars are still, well, too young to be fusing any elements in their core. So the interior luminosity that is coming from the protostellar interior is quite weak when compared to the accretion luminosity. And so what happens is that by looking at the luminosity of protostars, well, you can sort of use that as a prognostical tool to infer how quickly your protostar is accreting. And one parameter that goes into this accretion luminosity is the radiative efficiency parameter. It's essentially the fraction of the incoming kinetic energy that is actually radiated away. And as you'll see, this radiative efficiency parameter here plays a pretty important role in a number of different fields in star formation, essentially. So just to begin here, I'm going to give you a little bit of context to what originally motivated us in all of this. And the original motivation was obviously luminosity problem, which has a classical form and a modern form. So the classical luminosity problem was first identified by Kenyon back in 1990, and he had an observational survey in the infrared of some young stellar objects, and he discovered sort of a discrepancy between the observed protostellar luminosity and what you would predict through theory. So at the time, we thought that protostars would be typically built up between 100 and 200,000 years. And if you use that typical star formation time, well, you should expect um, sort of a mean or median protostellar luminosity that lies in between the 10 to 20 solar luminosity ranges. Except in the observational survey of Kenyon, he had a median luminosity of just one solar luminosities. And later on, we had surveys from the Spitzer Space Telescope that confirmed this low protostellar luminosity function value, sorry. And there were two sort of proposed solutions to this classical luminosity problem. The first one was the longer formation times, and the second one was episodic accretion. So first on longer formation times. So instead of assuming that protostars form between 100 to 200,000 years, people thought, okay, well, maybe they're actually forming on longer timescales. So the average mass accretion rate that they receive should be somewhat lower. And indeed, more modern surveys confirmed that stars form typically in 500 to 700,000 years. And by doing some extinction corrections as well, the median luminosities of protostars was increased from 1 to 5 solar luminosities. And if you consider that there's about a 25% mechanical energy loss through mechanisms such as outflows or protostellar jets, well, then you can make the theoretical protostellar luminosity fall in the observed range. So based on observational revisions and sort of the theoretical adjustments, while Offner and McKee considered the classical luminosity problem to be solved back in 2011. But today we have sort of a modern luminosity problem. So while the median protostellar luminosity can be explained by longer formation times, as you can see in this survey here, the protostellar luminosity function sort of has orders of magnitude in spread. Okay, so we're talking about 4 orders of magnitude in spread here. So while we can explain the median values here, in order to explain this huge spread in protostellar luminosities, we need episodic accretion. And essentially what episodic accretion is, simply the fact that, well, we're more likely to observe protostars in quiescent periods where they're not accreting much in between in between shorter periods of more bursty accretion. And from a theoretical standpoint, we know of multiple physical mechanisms that can give rise to episodic accretion. So, of course, we've all heard of the magnetorotational instability. So this is and this will lead to instabilities in the accretion funnels that feed the protostar in the innermost edge of the disk. Of course, we have gravitational torques. So the disk is, the disk around the protostar is self-gravitating. So that can lead to bursty accretion. And we have also large-scale variability. So essentially, the parent cloud that is feeding the protostar can itself be quite turbulent, and that can lead to large variations in mass accretion rates. And all of these models that attempt to explain, well, the protostellar luminosity function, they all assume that all of the incident kinetic energy at the protostellar shock front is going to be radiated away. So they're assuming a radiative efficiency parameter of unity close to 1. And of course, not only do we need to track down the radiative efficiency to, well, explain the protostellar luminosity function, but we also need to constrain it for pre-main sequence evolution. And in pre-main sequence evolution, what they have is this alpha parameter here, which represents the amount of energy that is accreted by the star. So in PMS, they're studying the protostar, so they don't really care about the outgoing radiation. They care about the incoming energy. And so it's 1 minus the radiative efficiency. And here in this paper from the 80s, you have different evolutionary curves of a protostar, assuming a different alpha parameter. So if the protostar is undergoing something that is known as cold accretion, where the majority of the incident kinetic energy is radiated away, you can see that it follows sort of a steady radius over time as it accretes material. But if you crank up that alpha parameter, so if you inject more and more of that accretion energy in the internal energy budget of the protostar, well, you can see how it can subsequently swell up quite dramatically. And in order to explain observations, well, the PMS community, well, they need something known as, well, cold accretion. The majority of that kinetic energy has to be radiated away. So they need a radiative efficiency parameter that is close to 1. But also they need a time varying alpha parameter. So the radiative efficiency over time has to vary because that will better explain the lithium abundance ratios in observations. Now, there's also an effect of radiative efficiency on the IMF. So if protostars are more efficient at radiating away the incoming kinetic energy, so if you have about 50% radiative efficiency here, you can see that the peak of the IMF will get shifted towards higher masses. Whereas if it's lower, well, that peak is shifted towards lower masses. And the explanation for that is quite intuitive. If your protostar is shining more efficiently, well, it's heating up the surrounding material more efficiently. So that inhibits fragmentation. So the radiative feedback of protostars is quite important if you want to understand larger scale structures and larger scale dynamics. I forgot to cite the paper here. This is the Henneville 2020 paper. I apologize. And then you have more subtle effects of this effect parameter on non-ideal MHD effects. So this here is the result of a simulation that included MHD when modeling the birth of a protostar. So you have the ideal MHD curve, which is in red here. So it's a magnetic field versus density distribution. And you have non-ideal MHD, where they include ambipolar diffusion and ohmic dissipation here. So you can see that the strength of the magnetic field is very much impacted by resistive effects. And here it is quite subtle, but the dust resistivity, which really dictates the strength of magnetic resistivity, is quite sensitive to the temperature structure. So if you want to accurately model those resistive effects, you need to accurately model the temperature, and so you need to better constrain your radiative efficiency. And then, of course, that is going to have an effect on the disks. So here we have a simulation by Le Breuil and collaborators where they take a giant molecular cloud, they make it collapse under the weight of its own gravity, and that forms a whole population of circumstellar disks. And in those models, they use sink particles to model the protostar, and of course, they prescribe radiative efficiency. So here you have the radius of those disks as a function of time. So star formation efficiency is analogous to time here. And I want you to focus on two curves, so the orange and the blue curve, because those two models have different radiative efficiency parameters. So the orange one has 50% radiative efficiency. First thing you'll notice is that disks appear to be somewhat larger when the radiative efficiency is higher. And the reason for that is quite simple. As you heat up the disk, you increase thermal pressure support and you puff it up. And not only that, but also, again, remember that the peak of your IMF is shifted towards higher masses. And so those higher mass stars will tend to have bigger disks form around them. And then here, you have the temperature structure of the disks. And no surprise here, you have about a factor 2 hotter disks in simulations with higher radiative efficiencies. So if you're interested in planet formation, for instance, you know that that is going to be something that is quite sensitive to the thermal physics of your disk. And so the radiative efficiency parameter obviously plays a role there. So our goal here was to sort of nail down that radiative efficiency parameter. Okay, so we need it for the prognostics of protostellar buildup to interpret the observations. We need it in pre-main sequence evolution, where they have an ad hoc assumption of a radiative efficiency parameter that is close to unity. Remember cold accretion. We need it to understand the IMF, and obviously we need it for disk physics. But in order to constrain the radiative efficiency parameter, we need to be able to resolve the protostellar shock front. We need to study the radiative behavior of the shock front itself. And that is an immensely challenging thing to do. And the reason for that is there's sort of a tyranny of scales here. So I'm going to briefly explain how a protostar is actually formed using this temperature density diagram here. So let's start off with a dense cloud core that's about to undergo a gravitational collapse. The first phases are going to be isothermal because the compressive heating that is generated by the collapse is going to be radiated away by dust grains. And eventually the gas becomes so dense that it's optically thick to its own radiation, so adiabatic heating begins. And that will form a first Larsen core that has a radius of about 5 astronomical units. And this first core is going to accrete materials from its surroundings. And so it's going to continue to contract adiabatically, first with a polytropic index of 5/3, which then switches to 7/5 once the rotational degrees of freedom of H2 molecules is excited. And then at some point, the central temperature of the first core reaches 2000 Kelvin. And when that occurs, the polytropic index of the gas drops to 1.1 because of H2 dissociation. So that's an endothermic process which consumes about 4.5 electron volts per molecule. And so the gravitational binding energy that was being injected into the thermal energy budget of the first core is now being spent up by this endothermic dissociation process. And as a result of this, the first core loses its hydrostatic equilibrium because 1.1 is below the critical value of 4/3 that is needed for stability against collapse. And so a second collapse ensues. And the second collapse is really the challenging part to simulate here. And once most H2 molecules are dissociated, a protostar forms because thermal pressure support goes back up, and then a disk will form around this protostar, and then the whole system transitions towards the empirical class 0 and class 1 phase. So just from a numerical standpoint, well, you can see that this is going to be difficult to simulate because we have about 25 orders of magnitude in density and 8 in spatial extent. So we're going from dense core scales, that's about a few thousand AU, all the way down to protostellar scales. So that's a few solar radii. And there's multiple relevant length scales that we need to resolve. So during the first collapse, we need to resolve a gene's length, and then we form a first core, and so we need to resolve the pressure scale height within the first core. But then the first core collapses in on itself, so we're back to resolving a gene's length, and then we're back to resolving a pressure scale height in the protostar. And once we form the protostar, the time step drops to the order of minutes, essentially. So this is extremely computationally demanding, all the while um, um, simulating the parent structure. And to top it off, we need to account a variety of highly nonlinear and complex physical processes. So we need to describe self-gravitating hydrodynamics and, of course, radiative transfer with a realistic equation of state that accurately models all of these phase transitions. And, of course, in most models, we will need to include magnetic fields. But what we're interested in here is, in particular, the radiative transfer, because we want to measure the radiative efficiency. So just in terms of uh, previous work in the literature, there's really well, there were 2 papers that reported the radiative efficiency of protostars. So I'm showing you the results of the Vaitain collaborators paper, which was a second collapse simulation with all of the relevant physics, including magnetic field. So you can see that they nicely resolve the protostar. And what they did here was they measured the radiative efficiency of the protostellar shock front, which you can see here. So it's the ratio of the outgoing radiative flux to the incoming accretion energy flux. And you can see that it's completely blue. So green here are outflows because their protostar is expanding. But for the most part, it's completely blue. So that's what we call a subcritical shock front. The radiative efficiency is below unity. Now, there is an anisotropy here. The polar regions seem to be radiating more efficiently, but they're still blue. So this seems to be at odds with all of the other previous models that I showed before, which rely on this ad hoc assumption of a supercritical shock front, so where FAC is close to 1. So to solve this, well, we thought that we simply had to make those calculations run much further out in time. And so what we did was we combined the 1D and 2D simulations that were carried out in Pluto by Asmita in her 2018 and 2020 papers with my 3D simulations, which were carried out with Ramses. And these simulations, they all have a similar physical setup. We're doing radiative hydrodynamics with gray flux-limited diffusion approximation. Okay. And we have roughly similar initial conditions. Asmita was using a Bonner-Ebert sphere. I was using a uniform density sphere. But when you're looking at protostellar scales itself, since the protostar results from the collapse of a first Larsen core, the results were qualitatively similar, and you'll see how they differ quantitatively. So the 1D and 2D simulations of Asmita were carried out in spherical symmetry. So the collapse was spherically symmetrical, and my 3D simulations were carried out with some rotations. And you'll see that that leads to qualitatively different results in the radiative efficiency. So these are sort of the governing equations that we used. So this is pretty standard. We have a continuity equation, a momentum equation, an energy equation, an equation for radiative energy, and self-gravity. And this is the standard radiative hydrodynamics with FLD. And we're going from first principles here, just going from these conservation equations and self-consistently forming the protostar and then studying the behavior of the shock front. And in order to resolve the shock front, obviously, we need very high resolutions. So we're talking between 10 to the minus 5 to 10 to the minus 4 AU. So that's a few dozen thousand kilometers, essentially. Now, here's an illustration of Asmita simulation. So this one here is 2D. Now you can see the grid. She used a nested logarithmic grid here. So we're starting at 10,000 AU. I'm gonna begin the video here. So this, well, in here you're seeing the collapse of the cloud itself. So we're in the isothermal phase. And soon enough, in the central regions will come optically thick, and we're going to form a first Larsen core. You can see it has a radius of a few AU, and then this first core keeps on accreting, and then it triggers H2 dissociation, which forms the second Larsen core. So this is the protostar itself, which she is resolving here in beautiful detail. So here you can see the interior. The swirly lines here are the velocity vector field. So you can see that there's enough resolution to resolve turbulent motion inside of the protostar. And of course, this very high resolution allows us to analyze the radiative shock front in great detail. Now I'm going to show you my Ramses simulation. So this here is a column density image. And what you're looking at here in these white contours are adaptive mesh refinement levels. So every time we cross a contour, the resolution increases by a factor of 2. So zooming in from dense cloud core scales all the way down to the scale of the first core, which again collapsed in on itself and formed a central protostar, which is here surrounded by a circumstellar disk. Now, in terms of structure in the 3D simulation, since it's not spherically symmetrical, well, you can see how that results in a different radiative behavior. What you're looking at here are radiative flux slices seen in a top-down and an edge-on view, and each column is a different simulation. And what I'm trying to show here is that you almost always form a similar structure, that of a central protostar, which is surrounded by a circumstellar disk. And that is pretty much independent of initial conditions because this protostar forms from the collapse of the first Larsen core. Okay, and here you can see in these radiative flux slices, well, first the location of the shock front, because remember, at the shock front, we're converting kinetic energy into radiation. And so here, whenever you see this very bright outer outline here, that's the location of the shock front. And then in the edge-on views, you can see how in the poles, things seem to be a lot brighter than along the equatorial regions. So I'll come back to this a little bit later. But the challenge we had when writing this letter was, okay, well, how do we measure the radiative efficiency of the shock front? And so It's essentially just the outgoing radiative energy flux divided by the incoming accretion energy flux. And what we resorted to doing was a local measurement of this radiative efficiency parameter because of the anisotropic structure. Um, uh, it's a bit complicated to come up with sort of a fixed surface onto which we can make sort of an energy balance, and we resorted to a more local measurement. Now, just as a reminder, when you have a radiative efficiency that is much lower than one, that's when you have a subcritical shock front. Okay, so in PMS terms, that's hot accretion, and when it's equal to one, you have a supercritical shock front, cold accretion, which is what we're trying to prove here. The radiative energy is obviously going to depend on the radiative transfer model that you use, but in FLD, this is what it is. And then the accretion energy flux is the sum of the gravitational potential energy, the internal energy that's being advected, the work done by thermal pressure gradients, and the kinetic energy. Now, in the 3D simulation, we have sort of a more complicated structure with an accretion shock that envelops both the protostar and the disk. What I'll be presenting are polar measurements of the radiative efficiency parameter. Okay, I will show you the equatorial regions later on, but for the sake of clarity, I'm just going to be focusing on the polar one, which really represents the protostellar shock front. Now, these are the resulting radiative efficiency measurements. Here you have them as a function of time and as a function of accretion rate. The dotted, the dots here are measurements made in the 3D simulation, whereas the solid lines here are those from the 1D simulations of SMETA. And here the striking result is that it approaches one in and it approaches one very quickly. Okay, so in 1D models, most models have reached a radiative efficiency of one in about a few hundred years, essentially, which is in star formation timescales that is very short. And in 3D, it's even more striking. It happens in about 2 years, essentially. So although we begin strongly subcritical with the majority of the incoming kinetic energy that is simply being dumped into the thermal energy budget of the protostar, very quickly we transition towards a regime where the radiative behavior is supercritical, where the majority of that incoming kinetic energy is radiated away. And the behavior of these curves here is dictated by the physics of the collapse of the first core. So in the first rise here, so just in the 1D model, the rise that you're seeing here in radiative efficiency is due to the fact that as the first core is being accreted by the protostar, the density upstream of the shock front continuously reduces. So the optical depth upstream of the shock front is decreasing over time, hence why the protostar radiates more efficiently. So you have this very quick rise here that is due to the collapse of the first core, and then as the protostar accretes the remnants of the parent cloud core, that's when you transition towards this more quiet regime of slow accretion with a slowly increasing radiative efficiency. Well, slow in relative terms, of course, because we're talking hundreds of years here. And in the 3D model, it's a slightly different story. Here I'm going to show you an animation that shows density slices in a top-down and edge-on view. Here we have the mass flux, but I want you to focus particularly on the edge-on density slice. So you can see the protostar that forms and then the disk that forms in the equatorial regions. And in the polar regions here, you can see how material is very quickly depleted. Okay. And so the density upstream of the shock front, when you're looking at the polar regions there, it decreases, well, a lot more quickly than in the 1D model. So the 1D models, they sort of represent a benchmark case where the protostar is really struggling to radiate away the incoming kinetic energy. And in 3D, well, the polar regions, they offer sort of an escape route for all of that radiation. And so you have an anisotropy in the radiative efficiency of the protostar in 3D. So here you have measurements along the polar regions where you can see that a radiative efficiency of 1 is very quickly achieved. In all of these curves represent different models, and you can see that all of them have reached 1 in about 2.5 years. But then in the equatorial regions, well, while you do see that quick increase, you have something that looks more like the results of the 1D model, where you're still strongly subcritical a few years after the collapse. And this can be seen sort of on larger scales in the simulation. Here we have radiative flux slices at about 100 AU scales. T equals 0 here is the birth of the protostar, and you can see as time goes on how the polar regions become successively brighter, whereas the equatorial regions are still very dim. So that's because of the anisotropy and the radiative efficiency. And of course, you can also do a more global measurement of this radiative efficiency. So instead of doing a local measurement where you place yourself just upstream of the shock front in the polar regions of the protostar, you can define a fixed surface. So this was I think it was a 2 AU sphere on which I measure I integrate over the surface and over time the incoming and outgoing energies. And you can see that, well, right here you have the global radiative efficiency. You can see it increase the moment where local supercriticality is achieved. So when the protostar becomes, well, when the radiative shock front of the protostar starts radiating away very efficiently the incoming energy, that's when on larger scales radiation begins to escape much more easily. So in conclusion, what we did in this letter was validate multiple ad hoc assumptions that were made in the literature regarding the radiative behavior of protostars. We showed that we have a transition from a strongly subcritical to supercritical shock front in a few hundred years at most. And we hope that sort of the quantitative measurements of the radiative efficiency can then be used in the literature for any models that sort of want more fine-grained adjustments. So thank you very much for your attention, and I'll be glad to take your questions if you have any.